the gumchwana wa bantu. Easy, man. So listen, man. This is more the contour integral or residual integral. Okay? But now, why do they call contour? Why is it residual? How I'm gonna know in exam or how they're gonna ask you? Listen. You see, when you're primary school or grade 9, but started grade 7, 8, 9, so if you did geography, there's something called contour. So contour, I'm coming there, okay? Look, contour, look, for example, if you have a mountain, like this, a sharp mountain, like a hill, and you have this normal hill. So if you want to represent this, let's say from area view, from the top, if you had to draw this, look, this is how you draw as a contour. You see, this is very sharp, so you draw very close. You know what I'm saying? But the more you go down, let's say like this, you see, it kind of spread out. So if you go down further, you make it like this. Because you know what happened? You see, kind of. But at this one here, if you had to draw from the aerial view as a contour, see, it kind of widen from the top. So this is what you do. You draw like this. So you draw according to how. But you see, this side is more. This slope is more steeper compared to this. So you do this because this is more horizontal. It's like the slope is kind of this direction compared to this. That's why this is very close. So when it's too closer, the contour line, if it's too how I'm gonna say, I don't know how I'm gonna say this, you know, if it's too if it's more the vertical, close to the vertical, if this slope is more close to the vertical means you draw the contour line very closer. But this is kind of this direction, so you draw like that. You know what I'm saying? So okay, so now we see, oh, so we can also integrate this, so we can have some sort of the function. Okay, because look, man, in normal integration we know we can integrate quadratic function, like quadratic function, it could be linear function, and integrate trigonometric integral. You can integrate all this type of integral. But for the most cases, we haven't done something has to do with a cycle or contour. So that's what, but okay, so now most of this contour integral has to do with a complex number or complex function. How? Because look, if you did normal complex function or complex number, if you draw the function, if you draw the graph of the complex function, it's always like this in cycle format. Complex function is always like this. You know why? Because look, in any complex graph, we have a real, you see what I'm saying? We have a real and imaginary axis. This is imaginary axis, this is a real axis. So when you draw your graph, the graph is f of z, means function or complex function. Oh, this complex function, and in a complex function we have an imaginary axis and real axis. Imaginary has an I. So I don't want to waste a lot of time on this. Let's get to the business. So this is why they say Lorentz series. So for you to do this integral, you need to know something called Lorentz series, which I'm going to show you now, and how to do residual integration. So in exam, they might give you trigonometric integral, and they say integrate using contour integral or residual integral. So now you're going to have to change the normal integral, either trigonometric or whatever integral they have given to you, to the complex integral, means in the form of the complex number, means in the f of z. That's the first step before you do anything. You know what I'm saying? Now let's go to the residual theorem first before we start to solve the question, because I want to solve a lot of questions for you guys. Okay. So the residual theorem say, let z be the analytic inside the simple closed path. Okay, let's say you got a, let's say you have a path here. Let's say this is our contour, a certain path, which let's call this f of z. Means function, complex function. You see what I'm saying? So this is a closed path. Let's call C, means the path of this function, and let's assume is counterclockwise. Counterclockwise means this direction. Opposite direction of the watch, because the watch go clockwise, so counterclockwise opposite direction. So now, except for the finite many singular point. Okay, so if this is complex function, let's assume we have a lot of singular point. We have a lot of point inside here. Z2, Z3, Z for infinity many number of singular points. We got a lot of points. Z1, Z2, ZK means it's so many of them, so we don't know how many of them. Let's actually to infinity many number. Okay, now inside C, inside the cycle, then the integral of Fz, if I have to integrate, so you see now, so this is the contour integral. You know what I'm saying? It means if I want to integrate now, this my function or complex function of a cycle with respect to z, it always equal to the, you say 2 pi. You know what 2 pi meaning? 2 pi is something with the circumference of a cycle. So cycle circumference. So this, if you integrate contour integral of a cycle of a function, whatever function you have, which I'm going to show you now with example, with respect to z, equal to 2 pi I. So you take 2 pi, you multiply by I, and then you sum all these singularity. So we're going to sum where it starts from 1 means all this singularity start from 1 to k, residual z equal. So now let's assume we have a lot of singularities. So now okay, so for now it's a lot of them, right? So let's say z a lot of this z means the residual z equal to all the z, or whichever z is going to be inside the cycle. But for now we have a lot of them, that's what I say zi. But sometime in a question they're going to give, maybe you're going to find us in a situation where you have a z which is outside and z is inside. Well, I'm going to show you an example now. So what you do, you take the z which is inside the cycle, but for now we have a lot of them here, that's what I'm taking. Zi means a lot of them, and then function of z. So this is how you do. This is how the residual theorem says, which is the same thing here, just raw. Now let's continue. Whereby, except for finite many singular points inside the cycle, then the integral of f of z, taken counterclockwise, see, of f of z taken counterclockwise around c, around this c, equal, you see, equal to 2 pi, yes, 2 pi I times the sum of the residual of f of z at z1, z2, all of them. So equal to the sum means you sum, this means summation of all the residual of all the z of a function of z. You see what I'm saying? So this is the residual theorem, how you say it. So I'm going to raise here, and then I'm going to prove to you. And then after that, I'm going to go to the question. So I'm not going to waste a lot of time here. Let's get to the business. Okay. Residual theorem. So in other way, so now let's go to the proof now. It's just a 3-line sentence. So the proof, this is how to say in the proof. Listen here, man. Let's assume, for example, okay, let's assume, for example, I have a, oh man, this is not good drawn. Okay, let's assume I want to draw, I'm not good drawer, you know what I'm saying? Okay, so we know if the path, let's say we got path C, you know what I'm saying? In this path C, let's have a lot of singularity. Let's say this is Z1, let's say this is Z2, and this is Z3. You know what I'm saying? So if I can integrate a function or complex function of a cycle with respect to Z. Let's say cycle of a cycle of the whole cycle. It is same as integral complex of a cycle 1, because you can have a lot of subcycle or cycle, another cycle, another cycle. F of z dz plus integral of cycle 2, contour integral, you can say contour integral of cycle 2, sz dz. So you could have a lot of cycle with a lot of singularity. Maybe this is a cycle with a lot of singularity. There's another cycle with more singularity, just like how we see another cycle with more singularity. So you add with 3 to lot of them. So contour integral f of z d dz. So all these you're gonna add them to, let's say, plus, let's say this is 3, right? Let's say integral of ck, because it's gonna continue a lot of them, c1, c3, c4, c5 to ck. F of z, this is contour integral dz equal. So if you can add all of this, because according to the residue theorem, if this, meaning the sum of all those cycles, so this is one cycle, second cycle, and this is, let me say, 2 pi I, and then we sum, whereby I start from 1 to pi, and our res z equal, okay, the space not enough there, so I think here you're going to say, okay, let me write down here so you can see clear. So that's equal to 2 pi I, and then sum all these singularities. So you say j equal to 1 to chi, whereby the residual of dz means sum all this singularity of all these z1, z2, z3, z4, zi of the function, of complex function. So this equal to this. You see what I'm saying? So let's say here, so this is how you could prove. So I'm going to touch a little definition, so you know, so when you prove, then you can have something to say in your proof. You know what I'm saying? So now let's go to the question. For example, in exam, they might give a question like this. It's a very interesting question here. So I'm going to go quick a little, because now you understand how it goes down. So I'm going to go quick. Okay, now we have a question here. What a question. Okay, let's say using the residue theorem, I'm going to go quicker now, because now you got some idea using the theorem. So let's say integrate, start from 0 to pi, 0 to pi d theta over square root of 2, square root of 2 minus cos of theta d cos of theta. That's all. They say show equal to pi. Using the residue theorem, you need to show this by using the residue theorem. Show that if you integrate this, you're going to get that by using what? Residual theorem. So look here, man. So first and foremost, me personally, you know what I'm going to do? Like I said, I need to change this face from trigonometric to contour integral, or to residual integration. So first and foremost, I don't need this type of integral. It has to be contour integral. I don't need this trigonometric. I don't need that. Everything must be in a complex function. Now, let's go. So first and foremost, you need to know this. If you have cos theta in normal complex number I, sine theta, this is, let me say, E I theta. This is uniform. 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 So you need to know this. This is very important. It's Z equal, so you can say Z equal to this. So you need to know this one first before you do anything. This is in uniform. This one is in uniform, this. You see what I'm saying? So now we're going to say which is in a basic complex function. So we're going to say now z equal to e I theta. And the next thing is I'm going to differentiate so I can get what? D theta. Look, I'm going to differentiate. When you differentiate, this is going to give you dz. And when you differentiate e I theta, look, if you differentiate e function of x, what you do? You differentiate whatever is in here, you write at the back, and then we write exactly the way how it is. So I'm going to differentiate I theta because my intention, I want to get dz with theta because theta has to go. So I'm going to say, oh, so for that case, I'll have to differentiate this. Okay, let me just do this. D theta. D. Now let's just do straight. When you differentiate I theta, I'm going to get to I. You see what I'm saying? I'm going to get I because this theta is going to go. And then it's going to be E I theta. But what did I differentiate? I differentiate with theta. So put the respect to theta. See? Theta. And then after that, now I have to make the subject of d theta. But look, this equal to z. So before I go further, I'm going to say dz equal to I z d theta. You see what I'm saying? And I have to make the subject of d theta because I want to replace that. So it's okay, my d theta equal to dz over iz. So this is going to go there. So I'm going to say this one's here, this inner group face. Okay, let's just make a space here. Because I don't know my d theta, di equal to that. So I'm going to say, well, let me write here. So I'm going to say this is going to become inner group, but it's not normal inner group. Contour inner group for a cycle of path. D theta is going to become dz di. dz iz. dz iz over square root of 2 minus. But a cos of theta also, just make a space here. Just note, okay. Another thing, note, cos of theta equal to 1 over 2, you memorize these things, okay? Z minus 1 over z, plus 1 over z, my apology. But for sine theta equal to 1 over 2, z minus 1 over z. So for this time now, we don't need sine, we need cos. So I'm going to have to come and replace this cos so it can become in complex function. So I'm going to have to replace this here. It's going to become cos's, right? So 1 over 2, and then we're going to say z, 1 plus z. 1 plus z, okay. D theta, everything has been replaced. So everything has been replaced here. So now we're going to have to play around with this until we get to pi. So I don't need this anymore. So now this is what we're going to do now. First and foremost, I have to simplify this stuff here. I'm going to start with what is in something which is in here. So z plus 1 over z. If I have to simplify this, say over 1. Okay, no fraction. So what I'm going to do, z times z equal to z squared. Z times z equal to z squared. 1 times 1 equal to 1. 1 times z equal to z. Okay. So this thing here is going to be z squared plus 1. Okay. So let me deal with this face and that will bring it back. So say, okay, so this is same as say square root of 2 minus 1 over 2 bracket z squared plus 1 over z. And the next thing I can say 2 times z equal to 2z. So I can just 2 times z equal to z. So I can just say it's equal to z. 2z. But make sure you show all your works in exam, right? And I don't need this one because 1 times anything, you just say 1, so 2z. And next steps, I have to solve this now. I don't even need this. But I show all your steps. So I can say this is over 1 and then find the common denominator. Find the common denominator, excuse me. So now say this pi, take this, multiply there. So 2z times, it's going to become 2 square root of 2z. Okay? Now 1 times that, it's going to become minus, because minus is going to go in, minus z squared, and then minus 1, because 1 times something is same thing, over 1 times 2z is 2z, so 2z, so it's going to become 2z. So all the things are going to come in here. So let me say contour integral of a cycle dz, okay, dz, and then I Z over, you see what I'm saying? Now this is going to become, this is going to be 2z minus z squared, and then minus 1, and then over 2z. You see what I'm saying? So the next step now, I'm going to say, okay. So the next step here, look, I can take this to the bottom because look, I got this and this. So what happened? It's like somebody give you A over B, first fraction, then B over C. So what you going to do? So if means you're going to flip it. No, let's say this is K over C, K, D. So this, let me say AB divide by K, D. So this, let me say AB multiplied by D, K. So I can flip it. So I can say this is, let me say, so this, let me say, this is gonna go with that, and this is gonna come here. So dz is gonna go with this. So say, okay, so this is gonna be integral. Oh, I can write here. Okay, I can write here. So I can say integral contour. Let me go back a little bit. Contour integral of our dz, and these two z equal go there. Or I can just take, okay, look, there is a way I can take this one here, take this one right here, take this one right here. So take this one right here. So say iz, okay, iz, and I got 2 square root of 2. Or let me rearrange also this one, the one which is side. Let me start with the negative z square, and then plus 2 square root of 2z minus 1 over 2z. You see? So now the next step now, look, I don't need this z because look, this z and this z can cancel. So now I'm left with these two is going to go to the top. See the 2? Go to the top. So I'm going to say 2 go to the top, and then I can take outside because acceptable. This is a constant and this is a constant. But let me show you step by step because some people sometimes not. Okay, let's go. So 2 go to the top, and then we have an I, and then here we have a dz. And then here, let me take this negative out here because I don't want to have a negative z square here. Take negative out, so here I'm going to be left with z square, and then plus, no, it's not plus anymore because we take negative out, negative 2 square root of 2z, and then minus, it's not minus anymore, plus 1, plus 1. So what I'm saying? So that's going to be what? Plus 1. Here we go. So the next step, let me drink some water a little bit, guys, sorry. So the next step now, I'm going to say, take this one here. So I'm going to say this is same as, okay, I can do here, right? So I say, integral, I can take 2 out. 2i negative, let's take it outside. So this is dz. So what I'm going to do now, I can factorize this. See what I'm saying? Let's factorize. So when you factorize, let's do it aside, like normal factorization. So I'll say, but show all your works in exam. So we got z squared. Let me just straight me. I don't have to waste a lot of time. So I'll say z equal to negative b plus or minus b squared minus 4ac over 2a. So z equal to negative. What is that b? B equal to negative square root. Okay, so b equal to negative 2 square root of 2, and then because okay, plus or minus b squared. B squared means we take this and then we square. If you square this, is going to be 4, and if you square this, is going to be 2. So 4 times 2 equal to 8. So I can just plug 8 here. 8. Or take this all square. When you square to 2, 4, and when you square root of 2 equal to 2, 4 times 2 equal to 8. Minus 4 times a. A equal to 1, and c equal to 1. So it's going to be 4 times 1 is 1, times 1 equal to 4. 4 times, okay, 4 times a. What is the a? A equal to 1. Times c equal to 1. So just a 4. Over 2. 2 times a equal to 1. So just a 2. 8 minus 4 equal to 4. Square root of 4 equal to 2. So all this stuff is going to be equal to 2. So then, look, by 2, 1, by 2, 1, by 2, 1. So this is going to be negative, 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 positive. So no more negative. So square root of 2 plus or minus 1. That's our final answer. So our z, which are poles, equal to square root of 2 plus 1, or, so let's call this z1 and let's call this z2. Square root of 2 minus 1. So these are our z's. So I'm saying so-called singularity sometimes. Z, our z we got, which are poles, so z1 and z2, or you can call them singularity. So since I got this, you see, means, look, let me tell you something. This is very, very important. If somebody gives, let's say, x squared, somebody give x squared plus 4x. Let me take, let's say, just a second, right? Just a second, guys. I'm just want to do something here quick. Okay, x squared. Okay, for example, okay, somebody say solve this, but okay, use general formula. So if you have to use general formula, guys, look, okay, you're gonna say x equal to negative b. So negative b means negative is gonna be negative 1 plus or minus b squared means it's gonna be 1 minus 4 times a equal to 1 times c equal to negative 6, and then over 2 times a is like 2 times 1. So x equal to 1 plus or minus, okay, this is going to be 25 square root equal to 5 over 2. So our first value of x equal to, okay, 6 divided by 2 equal to 3, or 1 minus 5 equal to negative 4. Negative 4 divided by 2 equal to negative 2. So these are value of x. So if you want to factorize from your final answer, look, this is very, very important, right? You're going to say x, bring it back, minus 3, and then multiply, bring it back, x plus 2 equal to 0. So if you want to factorize from your final answer, you can always bring them back. So I'm going to use the same thing here. For my final answer, I've just got it. See, from the final answer, I just got it now. I'm going to say bring them back now. So I'm going to say now, my z, because the z equal to this and the z2 equal to that. So I'm going to say z minus square root of 2 plus 1 multiplied z minus and then plus 1. Oh, this is minus, my apology. Let me say it again, excuse me. So let's bring it back. So this is going to be z minus square root of 2 minus 1 and then z. See what I'm saying? And then z minus square root of 2 plus 1 equal to 0. So if I had to factorize, excuse me, this is the same as say this multiplied by this. So you know what I'm going to do? I'm going to take this stuff here, right here, and then come and replace this complex function. So show all your work in exam, show your work. That's how you get a mark. So I'm going to say, let's replace that a complex function. So I'm going to say, okay, I can erase here. Okay, so I'm going to say integral of, I can just do right here. Okay, integral of 2 negative I to negative I, and then I'm going to say my dz is just a dz. Okay, now, so this is going to be z minus 2 minus 1, and the second one is going to become z minus and then plus 1. Okay, so what is the next step? So when you reach here, then you introduce the residual theorem. You know what I'm saying? Let's go to our residual theorem now. So I'm going to raise this stuff here because you know how you get down. Let's go to our residual theorem and finish this question. It's easy, man. Residual theorem. Let's go to our residual theorem now and finish our question. So according to the residue theorem, it say, how the residue theorem say, okay, if you have an integral, contour integral of a function of z, which is this, you see this is contour, oh my god, of a function of z, dz, this is a function like this is the function of z. Oh, I can write here. Okay. This is the function of z. This one here. It's a function of z, dz of a contour integral. So this one we're gonna come and multiply later. Don't forget this is gonna come and multiply later. So we wanna sort this out. So this is the same as say 2 pi times I and then sum. Okay, j start from 1 to chi, but residual. Okay, our residual z equal. You see, residual z equal to all the z of a function of complex function. I mean a complex function. So this is a thing here quickly, just a minute guys. You see, we got two roots, remember, we got two roots. Before I change this, remember it was like this. Z, before I bring them back, it was z equal to, then bring back. Z equal to, let's go to, and then plus 1 and another z to z equal to, let's bring it back. It's going to be positive 2. And this one goes back, it's going to become negative 1. So this is your poles. So let's go z1 and z2. So you know what you do? You take the one which is inside the cycle. So which one is inside the cycle? The one which is inside the cycle is this one. See, like let's say you got a cycle like this, you say. So this is going to be outside the cycle. Take the one with the minus, because this is the one with the minus is going to be the singularity which is inside the cycle. So we're going to use this and not that. You see what I'm saying? So when they say here residual, but residual for what? A residual of Z2 for this case, because the one with the minus is the one which is going to be inside the cycle. So this is the residual I'm going to use, a residual of Z2. So when they say here res of what, take the one which is inside the cycle. So this is going to be lying inside the cycle. Inside the cycle. Or the poles, these are poles inside the cycle. Pole inside the cycle. Okay, now, so make sure you allocate this also, part of your solution. So now we're going to say, for this case now, so here we will add. So I'm going to say this one here, I'm going to just, okay, let me just say this. So I'm going to say this one right here, integral of my contour or cycle, contour of a cycle, function of z, this equal to pi I. Oh, so this equal to, so for this case, remember 2 over I is outside for this case. For now, so I can say, okay, so I'm going to come multiply later. So I'm going to say, okay, let me deal with this one now. Means this. Okay, so now I'm going to say, let's go. So I'm going to say integral. I'm not going to need integral now because I'm changing 2 here. So I'm going to say 2 pi I. You see what I'm saying? And then 2 pi I. Oh, excuse me. Yeah. 2 pi I. Okay, let's leave 2 pi I. We're going to come to do the 2 pi I later. Let's deal with this one. So I'm going to say my residual of z equal, but what? Z equal to Z2 for this case. Or don't say Z2, you can give it straight away. Like how we say, which one's Z2? Z2 was the one with it. I forgot. Okay, take that. So Z1 equal to, I want to know which one you chose inside the cycle, which is outside the cycle. This is equal to 2, because when you take back it's going to be positive, and this is going to be positive. Oh, so this one. So this was inside the cycle. You know what I'm saying? So I can say Z2. Z2 of a function. What is a function? A function is 1 over. Or if you don't want to say this, you can allocate exactly. What is a Z2? Z2 equal to? So it's not just because it's Z2, it's just because it's inside the cycle. Okay? Excuse me, guys. Okay, now we're gonna say Z here. We use another color. Z minus square root of 2 minus 1. Z minus square root of 2 plus 1. So what we're gonna do now? We know the value of Z, the one which is inside the cycle. We have to substitute in here. So let's substitute. So I'm gonna say our raise, or you can say equal to, because you know, so now since I'm substituting, I don't have to write raise. Equal, because like a limit or sum. So when you substitute, you don't have to write. So 1 over, let's substitute here. Square root of 2, instead of this, we say square root of 2 minus 1, and then we still have a minus square root of 2 here, minus 1, and then here we have the same thing here, Z we know, square root of 2 minus 1, and then square root of 2 plus 1. So what happened, look, some of these they're going to cancel, look. This and this cancel, so here we're going to have a negative 2, and this and this cancel, this and this cancel. So it's like, all these equal to 1 over negative 2. Oh, so all this stuff here, we know is 1 over negative 2. So now let's finish. So we must multiply with this. So we're going to say then, so it's going to come on 2 pi I multiplied by 1 over negative 2. But remember, so this is this. But remember, you still had this number here, 2 over negative I. So I'm going to say all this stuff also multiplied by 2 negative I. Now let's cancel some of the stuff here. This I and this I cancel, okay? 2 and 2 cancel, okay? Negative and negative become positive, so we left with 2 times pi. So it's 2 pi, and we have already proved. You see what I'm saying? So we have used the complex number using residue theorem and everything I've shown you, and we have proved that this integral given in trigonometric integral has been converted to complex function, and using residue theorem, finally we have proved. So you can see we have shown. Shown. I want to say shown. Come on now. What am I doing, man? Shown. Has already shown. Easy, man. Easy. It's just a waste of time. When you do this question, and it's easy like that, man. Thanks a lot. You know what I'm saying? Look, man, I believe in learning from how to do things. If it's make sure you subscribe, and you know, you can just go and do donation to our Patreon page. I have a Patreon, I have a GoFundMe. You know what I'm saying? I have all the means of donation, because to make this project going, you know, any type of donation, the little that you think is too small for you, it could make a lot of change. And thanks a lot for all your time. You know, subscribe, don't forget, share this video, circulate to a lot of people, you know, because the meaning of this project, this program, is to help as many as we can, okay? It's not only for one person or two, because you might think it's not helpful for you, but for somebody next out there, it could be very, very helpful. So thanks a lot, man. And you know, any donation that you did to me, it means so much. I appreciate it, man. It means a lot. Go to our Patreon page, go to our GoFundMe, because we need to have you know, a lot of things. We need to put them together, like camera, you know, and a lot of equipment, so that we can improve on, you know, a lot of angle, a lot of aspects of these projects. You know, thanks a lot, man. I appreciate and I love you. Peace, man. Bye. You know, this is one of my students of knowledge. You know, she wanted to introduce herself. What's your name? Could you please introduce yourself?
My name is Kali.
Yeah.
I go to Southend Primary School.
Yeah, China Wabantu. China Wabantu is everywhere, right? So this is my other student. His name, what's your name? Matthew, yeah, he's grade 11, man. So his aim is to score distinction, right? So you promise I want you to score distinction this time. And what's your name?
Joshua.
How much you promise me to score this time?
Distinction.
Distinction. Yeah, so China Wabantu is everywhere, man.
China Wabantu. Everywhere. China Wabantu.
Exactly. Thanks a lot, man. Appreciate it. Thanks so much.
Soldier,
advice, or which advice would you give to the people or to the students?
Trust Hamish.
Why would they trust you?
No, because it's really good. It actually has helped a lot. I redid first year for maths. It was my own fault, but also I didn't know a lot of the work. And Hamish said lots of hard questions, and it's demotivating sometimes to do the harder stuff. You like just want to get done, but it's the hard stuff that makes you realize the easy stuff is easy.
Thank you so much, Mr. Hamish. Thank you, and wish you all the best with your hard work. And I just want to say we appreciate you, and I have achieved like 93%. Sanmanani. This is Umar Nokulawam Kizismongo. I live in Devon in KwaZulu-Natal, and I was born in KwaHlabisa in KwaZulu-Natal.
Hello everyone, this is Uketele Nomvalo from Johannesburg, Midrand. I'm studying Trudy. I would like to thank Mr. Hamish for helping us so much. We have actually got 90 to 100% on that. Thank you so much, Mr. Hamish. Siyabonga.